In this video, we're going to look at how to draw Lewis structures that represent covalent compounds, which, unlike ionic compounds, share valence electrons between atoms rather than transferring electrons from one atom to the other. We can recognize whether atoms do this based on the difference in electronegativity between the atoms. For example, if you look at your periodic table, hydrogen has an electronegativity of 2.2 and carbon has an electronegativity of around 2.6, meaning the difference of electronegativity between carbon and hydrogen comes out to 0.4. This is an example of a covalent bond that forms between carbon and hydrogen because it is less than 1.7. Any pair of elements with a difference in electronegativity greater than 1.7 is considered to be an ionic bond. Less than that is a covalent bond. In terms of the steps for how to draw covalent Lewis structures, the first two are actually exactly the same as ionic Lewis structures. We start by drawing the Lewis structures of the atoms, meanwhile counting the total number of valence electrons that are involved in bonding between those atoms. Whenever we draw polyatomic ions, which will come later, we also need to consider the charge of the molecule that we're drawing to see whether that molecule has gained electrons or lost electrons from before. After we know what all of our atoms look like, we need to find the central atom of the structure, and as with ionic Lewis structures, the central atom is always the atom with the most unpaired valence electrons, that being the most valence electrons that do not exist within a pair in the atom. So for example, hydrogen only has one, nitrogen will have, even though nitrogen has 5 valence electrons in total, it has 3 unpaired electrons because these two exist in a pair. Oxygen, even though it has 6 valence electrons, has 2 unpaired electrons here. So if the 3 elements were hydrogen, nitrogen, and oxygen, nitrogen is the one with the most unpaired electrons. Where these steps differ from ionic Lewis structures is the drawing of covalent bonds. So after we find the central atom and count our total number of electrons, we need to connect the central atom with the peripheral atoms by drawing singular covalent bonds between the atoms, followed by which we're going to add all of these types of electrons back on, which are what we call lone pair electrons, back to the atoms. So for those that are confused about how we do this, the easiest way is to demonstrate this through a simple example that we can do here. So if we take a look at water, let's draw the structure of the atoms of hydrogen and oxygen once again. We know that hydrogen has 1 valence electron and oxygen has 6. If we count the total number of electrons, hydrogen has 1, 2 hydrogens, 1 times 2 is 2 electrons, plus the 6 electrons that come from oxygen, means that we're working with a total of 8 electrons. We know that oxygen has 2 unpaired electrons, while hydrogen only has 1. Therefore, we're going to put oxygen in the middle and put hydrogens around the oxygen to serve as peripheral atoms. Next, let's connect the oxygen and hydrogen each with a single bond, representing 2 electrons that are shared between oxygen and hydrogen each. We know that each bond consists of 2 electrons, 1 from hydrogen and 1 from oxygen, and we have 2 bonds, which means that we have added 4 electrons. 8 minus 4 is 4. That means that there are 4 additional electrons that we need to add. We can figure out what these are because if we look at oxygen, oxygen has 2 lone pairs of electrons that it does not share with hydrogen, and we can put those back right now. If we do this, again, we added 2 lone pairs. 2 times 2 is 4, which means that we have 0 electrons remaining. The last thing to do to make sure our structure is good is to double check that all of our valence shells are stable. So remember that hydrogen, because hydrogen only has a 1s subshell, a full 1s subshell has 2 electrons. This hydrogen has 2 from the bond. This one has 2 from the bond, so both of our hydrogens are good. And then oxygen needs a full valence shell, which is 8 electrons 4 from the lone pairs, and 2 each from the bond. 2 plus 2 plus 2 plus 2 is 8, and so we are good. However, if we try doing the same strategy with carbon dioxide, we end up with a little bit of a problem. So let's follow the same procedure and draw the atomic structure of carbon and oxygen. We know carbon has 4 valence electrons and oxygen has 6. 2 oxygens, 6 times 2 is 12 electrons from the oxygen, plus the 4 from carbon means that we're working with 16 valence electrons. We know that carbon goes in the middle because it has 4 unpaired electrons. Oxygen only has 2. So let's put carbon in the middle and the oxygens on the periphery like this. Connect both of them with single bonds, 1, 2. That means that we just used 4 electrons, 2 electrons per bond. 16 minus 4 means that we have 12 electrons remaining. We know that oxygen has 2 lone pairs, just like it does in water, so let's put each of those lone pairs back on the 2 oxygens like this. 2, 4, 6, 8 electrons is what we added, which means if we keep count of our electrons, we still have 4 electrons remaining. Well, what do we do with the remaining 4? Well, if we follow our steps here, if there are still unused electrons after putting our lone pair electrons in, we can add a double bond. And a double bond, which is a little more complicated than just 2 bonds, but for now, if a single bond is represented with 1 line, so single bonds look like this, 2 lines would represent a double bond, which represents 2 pairs of electrons between. And again, we have 4 electrons, which means that we can add on 2 bonds. So let's add a bond here, and let's add a bond here. If we do that, let's count valence electrons and see that all of our elements have a full valence shell. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. And because the carbon has 4 bonds, it will have 2 electrons per bond, which is 2, 4, 6, 8. Again, we added these 2 bonds here. That's 4 electrons, which means that we have 0 electrons remaining. All of our atoms have a full 8 valence electrons, so our structure is good. If we try this third example, we see a similar problem occur again. Let's do this procedure straight through. Here are the atomic structures of hydrogen, carbon, and nitrogen. If we count the total number of electrons, carbon has 4, hydrogen has 1, and nitrogen, because it has a lone pair, has 5. If we add these electrons up together, that means we have 10 electrons in total. We see that carbon has the most unpaired electrons because hydrogen has 1, carbon has 4, and nitrogen has 3. So carbon is our central atom with hydrogen and nitrogen on the periphery like this. Connect both of them with single bonds. That just used 2 electrons per bond is 4 electrons. 10 minus 4 means that we have 6 electrons remaining. Now, if we put nitrogen's lone pair back on, that's the only lone pair in this structure. We just used another 2, which means that we have 4 electrons remaining. So we can add a double bond here, just like we did with carbon dioxide. That's another 2 electrons that we used, but that means we still have 2 electrons left over. Well, if we apply this same logic, if we drop these 2 electrons in and add a third bond in the same way that we added this second bond here, that means that we have no electrons left over, so all of our electrons have been used. And if we check valence shells to see whether they have enough electrons, hydrogen's 1s subshell is full. It has 2 electrons. Carbon has 2 electrons per bond, and 4 bonds is 2, 4, 6, 8, so it's good. Nitrogen has 2 electrons per bond, 2, 4, 6, plus the 2 from its lone pair is 8, so all of our atoms are stable and good. From nitrogen, there is this third rule, or this final rule, that we can add. If there are still unused electrons after adding double bonds, we can make another bond, which we call a triple bond. So again, if you see 3 lines connecting 2 atoms like this would be a triple bond. And if you follow all of these steps here, that should allow you to draw covalent Lewis structures. And if you follow each of these individual steps, you really can't get the question wrong. So on that note, I will leave you with this Lewis structure here, CH2S, to try. It uses every single one of the rules described above. Once you finish that, there are an ample number of practice problems that you can try after this before we get into some of the more unusual cases of drawing covalent Lewis structures.